Welcome to Chem 125, Advanced Organic Chemistry. So I am really excited to be here this quarter. This is a fun course to teach, and it is a fun course to learn in. I want to start today by going over the syllabus and a little bit about my expectations for the class, and then we're going to dive right in with Chapter 1 of the textbook. So this is the website for the class. I presume all or most of you have already checked this out. We're going to have all of our homework assignments here. You'll get your exams and answer keys. I'll post various materials for the class, like those handouts I directed you toward. We also have some links here. You may have noticed the video cameras in the back of the room. One of the things that I've been doing is putting my classes available on YouTube and I think iTunes U, and basically not only to us but to the whole world, which has been really, really fun because I get to hear from people all around the world and they benefit from it. But mostly it's a chance for you to go back if you miss a class, if you're out sick and you don't want to share your flu with us or whatever, or you simply didn't pick up something, it's a chance to go back. The videos will probably be about a week after the class, so a little bit later than, don't miss class. I mean, come here, seriously. It's a good place to be. But it's a good chance to catch up, or if you want a way of enhancing your notes, to do that. All right, I want to start by going over the syllabus here. And I'll put a link to the videos, probably right above class materials or right below class materials, somewhere on the page. Anyway, I want to start by going over the syllabus here. And let's see. All right, so here I am, Professor James Nowick. I set some office hours, and honestly, you can come by and catch me at other times. I'll make myself available then. You can catch me after class. If you're really desperate, you can phone up to my office and say, hey, are you in your office? Can I come by? I've got a burning question. Bunch of ways to get in touch with me. We have a teaching assistant, Stan Yu, who I have personally selected. Stan has been asking me for the past, year, whether you could teach with me in this class. And also a peer tutor, Sebastian, is spending a year in my laboratory, meanwhile acing our graduate courses and putting our graduate students to shame. And Stan and Sebastian are going to work as a team as teaching assistants with the discussion sections and having their own office hours and so forth. The textbook for the class. I have loved this textbook for a long time. I taught Chem 125 a bunch of years ago, and the textbook was the second edition by Stowell, and it was already getting old back maybe a decade or 15 years ago. And I was really sad because it's a great book. This book is concise, it's readable in a quarter. At the same time, it's terse. It doesn't waste your time with stuff you should know already. And it's just a lovely book. Fits in your hand, everything else. And it was getting old. And so when I found out that in 2015, in the spring of 2015, a new edition was coming out where a new professor, Anne Faberkowitz, had come to revitalize the book, I was so excited and I was really glad. I kept pestering the publisher to get a copy to me, and I have not been disappointed. So as I say in the syllabus, this textbook really starts with where your sophomore OChem textbook left off. And I think if you've already read Chapter 1, you'll see that basically everything it's talked about with nomenclature basically goes way beyond. And we're going to see this in all the different topics we cover: synthesis, reaction mechanisms, and so forth. Which means your sophomore organic chemistry textbook is your friend to refer back to on all sorts of topics you might be a little bit rusty on. Honestly, I think the textbook and the problems are going to keep you pretty busy this quarter. But I know some textbooks, some supplementary books that I've used, that graduate students in my laboratory have used, that undergraduates have used, and they really love them. These are textbooks, they're not remedial. I've got textbooks to help. Well, the first one can help you out if you're a little fuzzy, but these are books to help really cement concepts if you're going on organic chemistry or if you just want more. Every graduate student I know has loved Bob Grossman's book, The Art of Writing Reasonable Reaction Mechanisms, great for curved arrow mechanisms and paracyclic reactions. There are two synthesis books, a textbook and a workbook, that are a lot of fun too. And I'm hoping that all of the problems, I hope you like working puzzle problems, because these really are making you think and getting you to think about how reactions occur and how you build molecules. And that's the same for the problems in this book. Okay, we've got the website, the lecture hours. There are 3 discussion sections. They should all be pretty similar, so it doesn't matter which one you come to, but you need to come to one. And we're going to go over things like homework and maybe get some extra problems in there. All right. Basically, as I say here, coming to class really is necessary. The textbook is dense, the textbook is challenging, and what I'm going to try to do is make sense of it. I like this text very much. This textbook is 10 chapters. We're going to do 10 chapters in 10 weeks. First 2 chapters are really short. We'll do them in 1 week. And I think you're going to get my spin from the class. I'll be listing reading assignments as we go along. I may already have listed all of them, and I will then list homework assignments from the chapter. All right, this particular, organic chemistry in general, but in particular this class, is something that you learn by working problems. And you also get to see the level of expectation that comes from working problems, and that is the most important thing for learning. In other words, you cannot master organic chemistry, and certainly not at this level, without actually working problems. So I've worked the first homework set. I will be working all of them. I have worked in the older edition them. These are fun. These are actually fun, tickling, challenging, engaging problems. It should take you some hours to work these problem sets. And they should be, I'll say for chapter 1, it's basically go back to the chapter and reinforce things. I read chapter 1, and every line I read where I saw a structure on nomenclature, I went back and it's like, okay, the answer was, how they got it was right here, and I sort of actively engaged with it. And then the homework problems, it's the same thing with that. You basically go back and you actively engage. Chapter 2, I've already worked most of the problems there. It is like a scavenger hunt in terms of finding information and learning the chemical literature. And as I said, this is taking us beyond where we started in sophomore organic chemistry. This is making us realize that chemistry is a living, breathing field, actively under development. Most of the remaining chapters are going to have not an answer key, but references to the primary literature, references to articles in Journal of Organic Chemistry and Journal of the American Chemical Society and tetrahedron letters and so forth. Most of those papers don't have a, quote, answer, but if you read those papers, along with work the problem and read or skim those papers, you will learn a hell of a lot. And I've done that in the course of my education, and this has been fun and engaging, a completely different experience from sophomore organic chemistry. All right, the textbook is the course is going to be very problem focused. And what that means is things have to get from here into here onto your paper. And that means actually working the problems. At the same time, working together, comparing answers can be a good thing. I approve of that. talking to the teaching assistants can be a good thing. But ultimately, the homework isn't about getting the right answer. It is about that process of transforming your thinking and your understanding so that you can actually really generate this knowledge and master it. So let's see. One of the things that I thought about, this is, as I say, I like this textbook. I really do. And the homework problems I've assigned are sort of the minimum for mastering things. It's sort of the baseline. There is so much more to learn. The textbook is, for the most part, pretty sane in its number of problems, pretty non-repetitive in them, which I think is good. In other words, they don't get boring. And so what I'm going to do, and again, this comes right back to the way I learned a lot of chemistry, is the more problems you work, the more you're going to learn. And I'm going to reward you for that. Right now, my plan is basically all of the exams and problems are going to be taken directly from the homework or adapted from it, meaning made in a more suitable format for an exam. I'll let you know if that changes, but right now I'm pretty gung-ho on that, which means you have the potential to go into an exam having worked every problem there, and for you it to be super easy. We're going to have 2 exams, so we're going to have homework. You've got to hand in the homework, and I think I'm collecting the homework at the end of class. We're going to work out on days that I've noted. I think we'll probably do it with a box or something in class. For getting the homework back, I'm still thinking about the logistics. My inclination is to basically have them go back in discussion sections. Maybe if we can set up some folders and alphabetize. It may get too chaotic, in which case we'll figure something else out. Okay, so that's 10% of the class. The midterm is 40%. We're going to run midterm number 1 is chapters 1 through 5 on Friday, May 6th, and then the final is Monday, June 6th, and it's going to be 1 through 10 comprehensive. All right, exams, I'm a little more clear about the mechanics, and we may end up doing, probably won't be able to do rapid return for the homework, so we'll figure that out. Anyway, the exams will be through the same electronic exam return feature that you're already familiar with. Going to have answer keys up, closed book exams, no makeup exam, unexcused absences counting as a 0. If you're going to miss an exam, like if you're sick, I need a note from a doctor, basically. Let's see, what else? Okay, don't cheat in the class. That just screws up the whole class it just sours it unbelievably. And unfortunately, at least in the sophomore class, I have failed a number of students. There is a policy here of basically any academic dishonesty results in a failing grade in the class, period. All right. Cell phones. I love my iPhone, but I absolutely cannot talk intelligently with beeps, chirps, rings, texting. Turn it off, put it to sleep. If it beeps, I'll send you out or otherwise embarrass you, or we'll focus the camera on you and put you on the internet of live embarrassing things, or send a picture to your mother or something, or I'll get out my phone and post you on the website, maybe. All right, all the enrollment stuff is handled by the undergrad office, and I think they have 2 weeks to drop the class. And it is going to be a hard class. And if you look at the first homework and the first couple of weeks and you say, oh my God, I'm just in over my head, come and talk to me if you're concerned, if it's to see if it's right for you. It's okay, you can figure things out. Anyway, I think it's going to be a good class. I think we're going to work really well together. Questions or thoughts on the syllabus? Yeah.
For homework assignments, will there be keys posted after they're due?
No, we will basically mark answers on the homework, basically a little correction or a little guidance on there. So no, there won't be keys present. Yeah.
If we're unable to make your office hours after 11 or noon, is there a way that we
Just
can schedule an appointment?
send me, easiest thing. Scheduling's a little tricky because it has the back and forth. I mean, if you say, are you available at this time, that's easy. Easy thing, pick up your cell phone, give me a call, say, are you in your office, can I come by? That's probably the most expedient, or catch me right after class.
Will any of the supplementary texts be available at the bookstore?
Art of Writing Reasonable Reaction Mechanism, no? No? Okay. Amazon?
Okay.
All right. How many people got the textbook at the bookstore, and how many bookstore? Amazon or comparable Barnes & Noble? So yeah, our bookstores, they mark things up hideously, which is sort of a shame here. All right. All right, so let's get going with some course content. So the way I teach this course is basically as a survey of advanced topics, the same types of topics that the graduate students get in their classes. In other words, we go into things that I think are important and fundamental to organic chemistry. Now, the first thing we're seeing in Chapter 1, although it's ostensibly on nomenclature, in other words, how you name molecules, what you're seeing in Chapter 1 is it really is about molecules. In other words, the molecules that you got in your sophomore class were simple representations, for the most part, of organic molecules containing the minimum amount of sort of extra material and the minimum number of functional groups. And we almost lose the beauty of it. We almost lose the beauty of the millions upon millions of ways, infinite ways, but right now we've got tens, hundreds of millions of known organic compounds, so we almost lose the beauty of that. Chapter 1, while it's on nomenclature, really is about the anatomy of organic molecules. And we're going to segue from Chapter 1 into databases, which is basically how we learn about real organic molecules. And we're going to go to the chemical literature. So that sort of is our introduction. That really is just our first week. Now, in terms of big ideas, the big ideas of organic chemistry basically become functional groups, stereochemistry, and reaction mechanisms. That is the overarching theme that ran across your sophomore organic chemistry class. And we're going to go into more depth. And we're going to move fast and assume that you've got sort of the basics of stereochemistry. But we're going to move into stereochemistry, which basically goes in and shows us the beauty of the three-dimensional structures of carbon-containing molecules and nuances like atrope isomers and other factors, other features that you probably didn't get in the introduction. It's going to be fun. We're then going to have a couple of chapters on organic reaction mechanisms. One of the big concepts, in fact, we have 2 graduate-level courses on reaction mechanisms. Although we don't have a graduate course on stereochemistry, I have a 1,400-page master work by Ernest Eliel, as well as a smaller 500 or 600-page work by him on stereochemistry. So it's a big and beautiful topic. As I said, we're just going to get a taste, a couple of weeks going deeper. Organic syntheses are going to represent functional groups and their transformations. and carbon-carbon bond forming reactions. And again, this is a topic that we have 2 graduate level courses on. You're going to go a little bit deeper on that. And then the last week of class, we're going to go into organic spectroscopy. Mostly NMR, but maybe a little bit of a review of IR, maybe a hair of mass spec. And again, we have a graduate level course on this topic. All right, so let us dive in to chapter 1 and start talking about nomenclature. All right, I am going to take as a given that you have, if not right at your fingertips right now, certainly the ability to refresh your memory on some basic nomenclature. So if I draw the following compound, who can give me a name for that? Octanoate, great. Fantastic. I am not mistaken here. In other words, you looked at this compound, you recognized that the most important functional group in it was an ester group. It's an ester of octanoic acid. It is the ethyl ester, and we name an ester, first name the alcohol part, ethyl, last name the octanoate part. And if we go ahead and play with that theme, we know about substitution. Oops, I'm going to draw this in such a way that it aligns here. All right, so playing with that theme, who else can give me a name for this molecule?
Would it be ethyl 8-methoxyoctanoate?
Perfect. Ethyl 8-methoxyoctanoate, all one word. In other words, you have looked at the molecule, recognized that the highest priority functional group is still the carboxylic acid functional group. Even though you see that you have an ether functional group, you know it's lower in priority. In general, the priority goes with oxidation state, so alcohols and ethers are lower oxidation state and priority than aldehydes and ketones, which are lower priority and oxidation state than esters. So you named it as a substituent, and you remembered that you number your chain from putting the functional group at the lowest number, 1, 2, 3, 4, 5, 6, 7, 8, and so forth. The other one that I'm going to take as a given, maybe with a little bit of dusting off, is that you can remember your Kahn-Ingold-Prelog stereochemistry. So this molecule's casual name is alanine. It's an amino acid. You can also call it L-alanine. It's the simplest amino acid with stereochemistry. But if we want to come to an IUPAC name for it in the same principle with a stereochemical designator, how do we name this molecule? Someone else. Okay.
2S amino, 2S2 amino carboxylic acid, propyl carboxylic acid.
Yeah, pretty much, yeah. S, we can put the designator. I think it can go in either place. I think it can go 2S or S2 amino propanoic acid. And honestly, the biggest principle I want us to take away on this, and again by way of review, is you're assigning authority, you're assigning priority to the atoms based on atomic number and then substituents attached to it and their atomic number, and citing down the bond to the lowest priority. So the stereocenter here, the hydrogen is the lowest atomic number, the lowest priority. The nitrogen is top priority. Of the two carbons, the carbon bearing the oxygens is higher priority than the carbon bearing the hydrogens. And if you want to get really into the nuances, which you may at some point have to, we count this oxygen as two oxygens with a double bond. So this is equivalent to a carbon with 3 oxygens bound to it. If we say had an aldehyde here, it would be a carbon 2 hydrogens, 2 oxygens bound to it. And so our priority goes 1, 2, 3. You cite down the bond. It's counterclockwise. And so you can assign it as S stereochemistry. All right. OK, all of that is sort of taken as a given for where our textbook begins. And I picked, by the way, on the homework, I tried to pick, I think, about 8 problems that I thought really catch the essence of the chapter. I don't expect this. This is a meaty chapter. Chapter 1 is meaty. I don't expect us to have 100% mastery of organic nomenclature. Don't get scared. What I want is for us to come away with a flavor of what all this nomenclature means. And I have a confession to make. In all of my graduate courses, I never had one time that really went through this, and I saw a lot of these names. And honestly, the first time I picked up this chapter 1 and just looked at it, basically, it's like so much of the stuff that I had been seeing for years made sense for the first time, not because I was a master and could do it all perfectly with my eyes closed or the book closed, but because having seen it once, it's like, okay, all this makes sense. Some of the stuff you just pick up along the way, and we're just going to, which I had done, but then some of the stuff like the benzo B, quinoline or something, actually it's like, okay, now that makes sense. Okay, so this is a cycloalkane. Anyone know the name of this molecule? Say it. Cyclooctane, great. No breaks in it, 2 O's that get up against each other. No hurt, no foul. All right, so where your textbook is sort of beginning, and I think it's a nice place to begin, is with bicyclic, or at least one of the places it begins, is with bicyclic molecules. So there's a bicyclic molecule, one that you might not have seen in sophomore organic chemistry. In other words, bicyclic, 2 rings. We have this bridge. If you want to get fancy, and usually I'm a slob in writing structures, if you want to get fancy, you put a little break in that line and back to show that you've got this line in front of this. I'm going to help you make sense of this structure in just a second. All right. So this compound gets named as a bicyclo. It still has 8 carbons in it. 1, 2, 3, 4, 5, 6, 7, 8. So it gets named as a bicyclooctane. We have 2 fewer hydrogens than cyclooctane because we have 1 more ring. And we call it bicyclo. And then we open a bracket and we say 3 period 2 period 1, close our bracket, all run together, octane. And it's sort of a cool example of what we call a bridged bicyclic compound. Now, it has a 3-carbon bridge, which is where the 3 comes from, a 2-carbon bridge, 1, 2, which is where the 2 comes from, and a 1-carbon bridge, which is where the 1 comes from. This drawing, very much like your drawings of cyclohexane, right? Everyone probably remembers this structure. And hopefully, everyone remembers that the reason a chair cyclohexane is drawn that way, or can be drawn that way, rather than just this way, is that when you put cyclohexane in a realistic conformation and look at it side on, that's what you see. That is a projection of the structure. One of the things I like to do in my sophomore organic chemistry class is take cyclohexane in a chair conformation, hold it on a big stick in front of the projector with the projector on white, and you will see on the screen exactly that structure projected with the axial hydrogens and the equatorial hydrogens and so on and so forth. And you can also draw cyclohexane this way. And similarly, we can go ahead and we can also draw our bridged bicyclic compound in various other ways. So for example, I can go ahead and draw it like so. And I'm just showing that it's a wedge, which means basically our bridge is coming up here out of the plane of the page, out of the plane of the blackboard. So there's our 1-carbon bridge, there's our 3-carbon bridge, and there's our 2-carbon bridge. So I would like to do the same for you that I do with my cyclohexane. And so I'm going to go over here onto our website. And let's see, I'm actually, I think, going to use that version of the website. And I try to share my class materials. Oops, helps if I turn on the projector. All right, so I try to share with the class the materials that I create. And this is a little demo I created on bridged bicyclic compounds and just a little bit of drawing to help show their structures. There's various software where you can view various file formats, and the file format I like is called a PSE file format, but the one that works a little bit better is the PDB file format. And all right, so this is basically, and I'm going to make this a little clearer. So this is basically the structure we are looking at here. It's what I've drawn. And I think you'll get to see the 3-dimensional shape of it a little bit better if I get to move it here. Maybe I'll kill the front light here. So I'll let that rock. And I want us to be able to relate this structure to the structure I just made on the blackboard over here, the drawing over here. And I think you can go ahead and see how that relates. So basically, what you're getting inside projection, what you're getting in profile, is this structure here. Now, the other thing that's sort of cool about this is if you look at this from a different perspective, and maybe I'll go to lines here. Okay, if you look at this from a different perspective, you can also realize, let's see if I can get that good for you. There you go. Okay, you should also be able to recognize that essentially what we have is a chair cyclohexane with a 2-carbon bridge across it like so. Anyway, all of these 3-dimensional structures really have much more meaning when you're able to visualize them in your head. I strongly urge you to go ahead and also get out your plastic models that you got with your sophomore kit and feel free to play with them. Now, the software I got is called PyMole. One of the cool things, I paid, I think, $760 for the license for it. One of the cool things about it is that it allows me to give it to all of my students for teaching purposes. So if anybody wants a copy, send me an email, and I'll give you instructions to link. Honestly, you've got a lot of other things on your plate, but if you want to play with those molecules or even build your own structures, you can. All right. Thoughts or questions at this point? Yeah.
With the bicyclic compound, do we ever observe that the ring that has 3 carbons pointing the other direction towards the 1-carbon bridge?
I think what you're saying, you're asking, is, oh, I understand. Yes. Okay, now I understand what you're asking. So when I was setting up to think about how I wanted to teach this to you, I decided to draw this in the most common realistic conformation. And so the question you're asking is, you look at this 3-carbon bridge down here, and you look at this bridge and you say it's banging into it. And this is a molecule where you are damned if you do and damned if you don't. And I'll show you exactly what I mean. Okay, so the short answer to your question, which is right on the mark, is yes. Okay, the short answer is this is another reasonable conformation, and they both have problems. Do you recognize this structure here? Boat, yeah. So this is a boat, which is bad because this hydrogen bangs into that hydrogen. There are a lot of other bad interactions as well. This is also bad because this hydrogen here, which is now right over the 3, bangs into these bridging hydrogens, but not quite as badly. But imagine we had a methyl group at this position. Then the lesser of the evils would be to put that methyl group there. So indeed, it can flip. And when it's really damned, for example, if you have a methyl group here and a methyl group here, what happens is this ring flattens out a little bit. And it gets a little bit more eclipsed, a little bit flatter than a regular cyclohexane. Absolutely insightful question, brilliant question. Other questions?
Maybe this is just a basic review thing, but what exactly is a bridge?
A bridge just means one. Okay, so let's talk about the anatomy of the ring. All right, so it is not a basic review question because you haven't seen this in your sophomore class. Okay, so here's our ring again. We call these joining points bridgeheads. And 3 bridges connect the bridgeheads. A 3-carbon bridge in this particular example, a 2-carbon bridge, and a 1-carbon bridge. Now, let's get into the details of numbering. So, bicyclics have a curious way of numbering them. We start numbering with the bridgehead. Then we number around the longest bridge. So we go 1, 2, 3, 4, 5, back to the bridgehead. 6 onto the next bridge. And finally on to the last bridge. So we number from the bridgehead around longest bridge then next and then shortest. We're going to see three, in the case of molecules today and next lecture, we'll see three slightly contradictory systems for three classes of molecules. We'll see one set of rules for bridge bicyclics, bicyclics in general, one for spirocyclics, and one for fused aromatics. Don't ask me why. All right, so now the smallest bridge defines a face. And so basically you've got sort of a convex face with the smallest bridge. And we call that face the exo face. I'll say is on the same side as the smallest bridge. So this is our exo face. So a hydrogen that's pointing onto that face would be an exohydrogen, just like you have an axial hydrogen or an equatorial hydrogen. The other face, if you will, sort of the concave face, the face opposite the bridge, is the endoface. And I would say, so this hydrogen here, we'll just call it H endo, and this hydrogen here, I'll call it H exo. And I would say these concepts that I've just laid out here, these are probably what I would call second nature to a practicing organic chemist. In other words, this level of knowledge, this basic sort of anatomy, oh yeah, that's a bridgehead, that's the smallest bridge, that's the endoface. That's probably second nature. Later on, when we talk about stereochemistry, I'll probably mention Brett's rule. Brett's rule is that in a small bicyclic compound, you can't have a bridgehead alkene, and we'll talk about geometry and why. In other words, I can't have a double bond, say, over here. It's too strained. And again, that sort of bridgehead alkene is probably an idea that would roll off most organic chemists' head. Yeah?
This may be a strange question, but wouldn't there be more than one face?
I guess you can say, okay, again, let's think anatomy. And let's come back to this drawing over here. So the biggest ring in the molecule is a 7-membered ring. So imagine now we're defining the top and the bottom of the 7-membered ring. So basically, the endoface is the bottom of the 7-membered ring. And the exoface is the top of the 7-membered ring. So yeah, there really are two faces. Now your textbook gets beyond this. Your textbook gets into tricyclics and so forth. And I guess my feeling at this point is for us spending only a couple of lectures on it, read it, let it pass over your eyes, see if you can make sense of the examples. But honestly, if you can get bicyclics down at this point, I'm really happy with that level of mastery. Have a look, though. When you're later along in your careers, you'll be able to flip back to that and say, oh, wait a second, I saw tricyclics once. I saw how you deal with additional features in the molecule. All right, I want to come back to some substituents here. And I'll give us a different molecule. I'll have a little bit of fun. Yeah?
Are you only able to like determine like if it's exo or endo through that chair conformation?
Regardless, even if it's flipped up. Even if it's flipped up, because it's because we're defining face opposite the bridge, this is still, that's still the endohydrogen. Even if the whole face isn't perfectly concave, it's the bottom face. It's the face opposite the bridgehead, and that's basically what's meant. You're welcome. All right. So, somebody, based on what we've learned so far, take a stab at this structure. What would we call it?
It'd be a bicyclo 321 6 bicyclo 321 6
2,2, yep. So bicyclo, so it's 7 atoms, bicyclo 2, 2, 1, hex. All right, and now we get to the numbering. So we've got two choices here. Remember I said number the biggest bridge. Well, we've got two choices. When all else is equal, we're going to give higher priority here. So it becomes bicyclo 221 hept, whoops, did I say hex? Hept 2-ene. Just like heptene, like when we say this molecule, we can call this 1, 2, 3, 4, 5, 6, 7. We can call it heptene. We can call it either 1-heptene or hept 1-ene. And I don't think it would be wrong to put the 2 dash here. I think there's enough freedom that you could call it bicyclo 221-2-heptene. Anyway, but you got the basic idea of it. It's still a bicyclic system. It's 7 now instead of 6. 2, 2, 1. Thoughts, questions? Yeah. Uh-huh. If it had been 3 carbons here, we wouldn't have been able to do it. We would have still had to number around this one. Now I want to show you one more set of variations. And we'll take the exact same molecule, except I'm going to put in an oxygen in the smallest bridge. And so now we go ahead. It's all the same principles, except now it is 7-oxa. So we use OXA, not to be confused with OXO. And it becomes, oops, no hyphen, bicyclo 2, 2, 1, hept 2-ene. And so oxygen gets oxa, OXA, not to be confused with OXO. N gets aza, and S gets thia. And again, these are terms that probably roll off the practicing organic chemist's tongue. All right, I want to show you one last example. It's going to be a bicyclic where we have no bridge on it. And we'll take all the ideas that we employed. All right, so This is a bicyclic without a bridge. It's actually a common reagent. It's called DBU. It is an amidine. It is a strong base. pK of the conjugate acid, 13.5, really good for elimination reactions. And all the principles we've learned can apply. It's got a 5-carbon bridge, a 5-atom bridge. It's got a 4-atom bridge. It's a total of 11 atoms. The U stands for undecene because we have a double bond. The D stands for diaza because we have 2 nitrogens. And the B stands for bicyclo. And again, all the principles apply. We start with the bridgehead, number the biggest ring, and its name becomes 1,8-diaza bicyclo. Whoops. 5,4,0 because we have a 0-atom long bridge. Undecene. So it's a strong base. The class of compounds where you have a nitrogen and another nitrogen together is called an amidine. All right, this is a very good stopping point for today. And these sorts of molecules that we're seeing here are the sorts of molecules that get me excited about organic chemistry because they're pretty, they're complex, and they show a whole bunch of ideas about how carbon and other atoms, nitrogen, oxygen, and sulfur, can be put together in myriad ways. See you on Wednesday.